Good day once again, everyone, and I want to use this opportunity to welcome you to the Physics branch of Mathematics Solutions Center. Today, we are going to be looking at a topic that says what? Equilibrium of forces. Under it, we are going to look at types of equilibrium of forces, resultant and equilibrant, triangle law of vectors, and we are going to solve examples under resultant and equilibrant and triangle law of vectors. So let's two types of what? Equilibrium. We have the dynamic equilibrium and we have the static what? Equilibrium. What is dynamic equilibrium? A body is said to be in a state of dynamic equilibrium when it is moving with a constant velocity, either on a straight line or in a circular path. So that's the definition of dynamic equilibrium. V is equal to what? Constant. Whenever a body is moving on a straight line or in a circular path with a constant velocity, then the body is said to be in a state of dynamic equilibrium. We can also define dynamic equilibrium as a state in which the body is not accelerated while moving either in a straight line or on a circular path. So when there is no acceleration, that means in dynamic equilibrium, acceleration is equal to what? 0, while velocity is equal to what? Constant. Velocity is constant in dynamic equilibrium. These are the two conditions for us to have dynamic equilibrium. What is static equilibrium? A body is said to be in a state of static equilibrium when there is no observable change in the position of the body. That is static. The body is stationary. Like if I have an object resting on a table, is that taken? We all know that this object has what? Weight. And the weight of the object is acting what? Vertically downward. But this object is seen not to be moving down, and it's not moving upward, and it's not moving towards the right, and it is not even moving towards the left. Then the body is said to be in a state of what? Static equilibrium. When there is no observable change in the position of a body, then the body is in a state of what? Static equilibrium. Take for instance, if I have this, if I have a balanced system like this, it is not moving towards the right and it is not moving towards the left, it's not moving upward and it is not even moving downward, then the body is in a state of what? Static what? Equilibrium. We are going to cover more about this in our next topic, which is what? Moment of what? Forces. Okay, watch out for that. I will do that video after this. What is a resultant force? Okay, a resultant force is that single force that can represent two or more forces in magnitude and direction. Take for instance, I have an object located at this particular point, and this object is acted upon by a force in this direction, and another force is acting on it in the vertical direction like this. We have a force trying to pull it in the horizontal direction, and we have another force that is trying to pull it in the vertical direction. You will find out that the object will end up moving in this direction, trying to satisfy the two conditions, moving both upward and what? Towards the right in the horizontal direction. Okay, if we can have a single force that will move this object in the same rate at which F1 and F2 is going to move the object and still satisfy the direction in which the two of them will move the object, then that single force that can act to replace these two forces, F1 and F2, is what we refer to as what? Resultant force. Therefore, by definition, a resultant force is that single force that can replace two or more forces in magnitude and direction. Or you can say that can represent two or more forces in magnitude and direction. That's what we mean by what? Resultant force. If I have an object, a force F1 moving in this direction and a force F2 trying to pull it in this direction, you can see from the line drawn for force F1, it is obvious that what? Force F1 is greater than what? Force F2. Therefore, the object will end up moving in the direction of what? F1, but not with a magnitude equal to what? That of F1. Because F2 is actually what? Reducing it. And our resultant force will be equal to what? F1 minus what? F2. Therefore, if F1 is equal to 5 Newton and then F2 is equal to 3 Newton, then we are going to have our resultant force is equal to what? 2 newtons. 5 minus 3 to get what? 2 newtons. This is for an object that is moving on a straight line and acted upon by two what? Parallel forces in the opposite direction. In a situation whereby we have an object is being acted upon by two forces, F1 and F2. Just the same thing, that F1 is equal to 5 Newton and F2 is equal to what? 3 Newtons. Therefore, the resultant force that will replace F1 and F2 and still produce the same effect as what? F1 and F2 will be given as what? 5 plus 3. So that means our resultant force will be equal to what? 8 Newtons. So this is a single force that can represent what? F1 and F2 in both magnitude and direction. So it is what? 8 Newton. And it will produce the same effect as F1 and F2. Now we can see that in the first diagram, in this diagram, you can see that the resultant force is gotten by what? Subtracting F2 from F1, because they are acting in the opposite direction to each other. And we can also see that what? In diagram 2, the resultant force is gotten by what? Adding F1 and F2. This is just to tell you that the resultant force will be maximum. So if we have two forces, F1 and F2, acting in the same direction, as in this case, F1 and then F2, their resultant will be what? Will be maximum when the two forces are acting in the same direction. In other words, we can say that what? Resultant force will be maximum when the angle between the two forces is 0 degree. Now, when the two forces are acting in the opposite direction, F1 and what? F2, the resultant force will be what? Will be minimum. So Fr is equal to what? Minimum value. That is, the angle between the two forces will be equal to what? 180 degree. Equilibrant. What is an equilibrant? Actually, equilibrant and the resultant force, they are equal in magnitude, but they are opposite in what? In direction. If a resultant force is going like this, then equilibrant will have the same magnitude as the resultant force, but moving in the opposite direction. Therefore, we can define an equilibrant as that single force that will balance two or more forces acting together. Just like a resultant force is a single force that will represent two or more forces in magnitude and direction, an equilibrant is a single force that will balance two or more forces in magnitude and direction. Anytime you are asked to calculate equilibrant, all you have to do, just calculate your what? Your resultant, and change the direction of the resultant. So whenever you have this, all you have to do, complete the what? The system to make what is called a parallelogram. And then you draw a line from their common point of the two forces. So this is my F2 here, while here is F1. Okay, the side, a parallelogram, opposite sides are equal and parallel. Therefore, if this side is F1, therefore here will be what? F1 also. Now let's state our parallelogram law of vector. Parallelogram law of vector states that if two forces F1 and F2 are represented in magnitude and direction by the adjacent sides, this side and this side, of a parallelogram, you can see the whole shape is a parallelogram. So if two forces F1 and F2 are represented in magnitude by the adjacent sides of a parallelogram, therefore their resultant can be represented in magnitude and direction by the diagonal of the parallelogram drawn from their common point. So we are just going to use this to solve a question. Two forces F1 equals to, let's say, 4 Newton and F2 equals to what? 5 Newton. Acting at a point. So acting at a point and makes an angle of what? 60 degrees to each other. Find the what? Number one, find their resultant force, and number 2, calculate their what? Equilibrant. That's what we want to look at. 5 Newton and then 4 Newton acting at a point. Now we want to find their resultant force. We are going to use what? Parallelogram law of vectors. Now all I have to do, I will complete this shape to form a parallelogram. I will transfer this line of 4 Newton parallel to it to the end of the 5 Newton line. And the same thing, I will transfer this also parallel to it to the end of the what? The 4 Newton. Therefore, I have my parallelogram, but I will continue this on a straight line. I will extend this line. Therefore, the angle I have here is also what? Angle 60, because this line, 4 Newton here, is also 4 Newton here. So, and they are parallel. Two lines are parallel when they have the same, when they make the same angle with a common line. So this is what? 4 Newton as well. And the angle here is 60. I can calculate the interior angle here. Sum of angles on a straight line here will be what? 120. So just by saying 180 minus 60, I'm going to get what? 120 degrees. According to the parallelogram law of vector, it said that what? The diagonal of the parallelogram drawn from their common point. This is their common point here, not drawn from here to here. That is not the what? The resultant, because it is not drawn from the common point, but from here to here. That will be our what? Diagonal. This is our what? Resultant that we want to calculate. Then let's extract half of the triangle. This is our resultant here that we want to calculate. R, here is 4 Newton, and here is what? 5 Newton. We are going to borrow a formula, which is what? Cosine rule, to find the value of R. And it is given like this. R square will be equal to what? 4 square plus 5 square minus 2 times 4 times 5, then cos 120. Take note of that. So I'm going to have my R square is equal to 16 plus 25, then minus 4 times 5, 20 times 2, 40, then cos 120. Therefore, we have our R squared is equal to what? 41 minus 40 times minus 0.5. We are going to have R squared is equal to 41 plus minus 40 times minus 0.5, that is plus 20. Then we are going to have R squared is equal to 61. Take the square root of both sides. Therefore, our R is equal to what? Square root of 61. R is equal to 7.8 Newton. We have gotten the value of R. That means the equilibrant is also what? 7.8 in what? In magnitude. So sometimes we can use a negative answer to indicate that what? It is moving in the opposite direction of the resultant. Now the next thing we need to calculate is, because it is a vector, you need to calculate the angle it makes with the what? Horizontal. Let's represent that angle with what? Alpha. Now we want to calculate alpha, which is the angle the resultant and the equilibrium make with the horizontal. Using sine rule, we are going to have 4 over sine alpha is equal to 7.8 over sine 120. So we cross multiply from here, and we have sine alpha is equal to 4 sine 120 over 7.8. Sine alpha is equal to 0.4441, and alpha is equal to sine inverse of 0.441. Alpha is equal to 26.4 degrees. So this is the angle, the resultant, and the equilibrant with the what? Horizontal. But both of them are opposite in direction, but they are what? equal in magnitude. Take note of that. The next thing we are going to be looking at is what? Triangle of forces. What do you understand by triangle of forces? The law of triangle of forces states that triangle of vectors or forces is still the same thing. Take for instance, this is F1 and this is an T2 and this is W. Now take for instance, we have this three-force system. We can represent these three forces with the three sides of a triangle, and that is what triangle law of vectors is talking about. So the triangle law of vectors states that if three forces acting at a point are in a state of equilibrium, then the three forces can be represented by the three sides of a triangle taken in order. We are going to represent these three forces the way you are seeing them in magnitude and direction by the three sides of a what? Of a triangle. So that is what triangle law of vector is saying. And number one thing you must always consider is that what? If we have weight of an object there, you should know that what? The weight of a body is always what? Acting vertically downward. Take note of this. Anytime you want to represent weight, it must be a straight line, a vertical straight line. And the direction will be what? Will be downward. That's how you represent a weight. Never you represent a weight with what? Horizontal line. It is very wrong. Never you represent it with an inclined line. It is very wrong. When you are representing the weight of a body, it must be represented with a straight line, vertical straight line, and with the arrow pointing downward. That is, the weight of a body is always acting vertically downward. This is number one condition of representing what? Three forces in with the size of a triangle. Number two, take note that you can change a pushing force to a pulling force, provided the magnitude and the direction of the force does not change. A pushing force can be changed to what? Pulling force. And vice versa. Take for instance, we have an object, this, that is being pulled by this force, 5 Newton. If I decide to what? Change this my pulling force to a pushing force, and it's still my 5 Newton. I have not changed the direction, I have not changed the magnitude. That means, number one, this and this is still the same thing because the same effect will be produced at the end of the day. Therefore, a pushing force can be changed to a pulling force, and a pulling force can be changed to what? A pushing force. And number three thing you have to put into consideration when you are working with triangle of forces is that what? We can transfer a force parallel to its line of action. Now, let me still use this same diagram. Take, for instance, I have this, and we have a force pulling it in this direction at the upper part, 2 Newton. I can decide to what? To change the position of this what? Force by bringing it down to this particular, towards the base. So I can change the position of my 2 Newton by bringing it down towards the base. It will still produce the same effect both in magnitude and in direction. Therefore, there's nothing wrong to that. So number three is talking about what? A force can be transferred parallel to its line of action. Take note of that. So we go back to our diagram and we are going to represent it what? In magnitude and direction by the three sides of a what? A triangle. Okay, this is what we have. And we want to represent it with what? In magnitude and direction. Actually, I can do this directly from the what? From the diagram. And I can decide to do it on a separate what? Space. Now I will start by what? Doing it on the same diagram. If I'm to do it on the same diagram, I can extend this my horizontal force backward and then transfer the weight back here. Then you can see that I have my triangle of force like this. This is the weight. This is the horizontal force F1 and this is my T1. So you can see that their directions have not changed. The weight is still acting downward. The T1 is still acting in the direction in which it was acting, and the horizontal force F1 is still acting in the direction it was acting. So I have represented it with what? The three sides of a triangle. Now let me do the one of drawing it in on a new space. The first thing, I will start with the weight. It's acting vertically downward. I will draw a line vertically downward. Okay. Now I will go to the end. I will think of which of the two other forces can I draw. I will just make sure I draw anyone I decide to draw in its direction. Okay. I will draw F1. So I will go to the end of what? My weight. And then draw F1 in its own direction like this. So this is my F1 still acting in this direction. Now, the main thing is that we want to draw a triangle and the triangle must be closed. So how do we close it? So that what? T1 will still be represented in its what? Direction. Is by drawing a line from the end of my F1 to meet the beginning of the line of action of the weight. Therefore, we have represented the three forces in magnitude and direction by the what? Adjacent sides of a triangle taken in order. Taken in order. And it can still be represented like, and I can decide to change this pulling force of F1 to what? A pushing force acting in this direction. And then my F1 is still like this to close it. The only way to be perfected in this in drawing your diagram is by what? Taking various examples. Okay, I will advise you to try as much as possible to try various examples. Okay, then you will be able to what? To represent forces in magnitude and direction. The highlighted part, a mass of 2 kg is supported by two cords, which makes an angle of 30 degrees and 50 degrees with the vertical. Calculate the tension in the two cords. Now, according to the question, this is what we have. Okay, so we have the weight of the body is acting vertically downward. All you have to do, draw a vertical line downward. Okay, and then if you look at this P is going towards this direction. So I can decide to draw my line to go in that direction also, either from the end or from the beginning. So I will go to the end of this my vertical line, which represents the weight, and draw an arrow in that direction. So that is my what? Let's say, and it makes an angle of 30. So the angle it makes is still that 30. And then the next one in the other way round is going in this direction. Therefore, it must be represented that same way so that the triangle will be closed. The triangle is now closed. Then we have this arrow to indicate its direction. And don't forget, it makes an angle of what? 50 degrees with the what? Vertical. The weight is what? Vertical line. So 50 degrees. So I have my T2 and T1 here. Let's calculate the angle here using the sum of angles in a triangle. Let's say 30 plus 50 plus alpha is equal to 180. Let's represent the angle with alpha. Therefore, alpha is equal to 180. 30 plus 50 is actually what? 80. Therefore, my alpha is equal to what? 100 degrees. Okay, we applied our sine rule formula, which is what? T1 over the sine of the angle opposite to it, which is what? Sine 50. And is equal to T2 over sine 30, that is the angle opposite to it, and is equal to 20. The weight of the body is 20 as given in the question, over sine 100. Okay, I can, because this particular fraction is complete, then I can combine this and this to find T2, and also this and this to find T1. Therefore, to get my T1, I will say T1 over sine 50 is equal to 20 over sine 100. All you have to do is to solve this and get the value of your what? T1. Therefore, I have T1 sine 100, we are cross multiplying, is equal to 20 sine 50. Divide both sides by sine 100. I have T1 is equal to what? 20 sine 50 over sine 100. Therefore, our T1 is equal to, so my T1 is equal to 15.56 Newton. The same thing with T2. I'm going to use T2 over sine 30 is equal to 20 over sine 100. T2 over sine 30 is equal to what? 20 over sine 100. Therefore, my T2 is equal to 20 sine 30 over sine 100. 10.15 newtons. Thank you for watching. We have come to the end of this tutorial. If you have not subscribed to this YouTube channel, kindly do that now. Thank you. Like this video, share it, and at the same time put on the notification button and remain blessed. Thanks.